Hey guys, how's it going? Welcome back. Well, today I thought we'd talk a little bit of science, I guess you call it. I don't know how many of you watch the show Through the Wormhole, but you know they're talking a lot about stuff in physics, quantum physics, time travel. If you went faster than the speed of light, then you're time traveling, which I think is wrong. Okay, speed is speed. The faster you go, the faster you get somewhere. Time travel, whole different ball of wax altogether. Anyway, so the other show that I've been watching recently on Through the Wormhole, they're talking about traveling faster than the speed of light. And as far as physics is concerned, or scientists, is that nothing can travel faster than the speed of light. So the speed of light that's it. It's an end all to be all. There's nothing that can go quicker. There's no way to make anything go quicker than the speed of light. So we should be able to achieve at least light speed. But to travel to, say, something that's 9 light years away, because they say if you take the speed of light and go by time, you can travel that distance. Would it take you 12 years, right? At the speed of light to go 12 light years. Well, as far as I'm concerned, I don't really think scientists really even know how long a light year is, let alone their calculations. I think are a little screwy. Just look at it this way. If the moon is, say, 250,000 miles away, and the speed of light itself, just the speed of light, is 186,000 miles per second. That means that in less than 1.2 seconds, you could get to the moon from Earth. So, at the speed of light. Now, how far away is Mars, or Jupiter, or Venus, or any of the other planets in our solar system? We could get there in a matter of seconds, going at the speed of light. So there's no boundary for us then in traveling throughout our own galaxy, or even going outside of our galaxy. It could take a while to get outside the galaxy, maybe, I don't know, a couple of hours at light speed. You gotta think. Think about a GPS, okay? Add that math in there. Your destination is 300 kilometers away. So if you travel at a highway speed at 100 kilometers an hour, it should take you about 3 hours to get somewhere. And 100 kilometers an hour is about 60 miles per hour, right? So 60 times 3, that's going to be 180, 240 miles total. So if you were going in miles per hour at 100 miles an hour, you could get there in 2.1 hours or 2.2 hours. So you actually can go there quicker if you want to. And we have cars that can travel 110 miles an hour, right? So you could actually do 330 miles in 3.5 hours at 110 miles an hour. So when you take into calculation of time and speed, let's take that same time and let's say we're going to go 100 miles per hour and we're going to travel 60 miles. How long would it take us to get there? Not very long. Okay, so because you can do 100 miles within 1 hour, so you're traveling 60 miles of distance, right? So you're going to get there definitely in far less than an hour, obviously, way less. Okay, so the faster you go, the quicker you can get somewhere. So at 186,000 miles per second, getting to the moon in about 1.1 second, that's pretty quick, for speed and time versus distance, because the moon is supposed to be 250,000 miles away. So if you were to make it to the moon in 1 hour, you need to travel 250,000 miles per hour to make it there in an hour. And you actually do make it in less time, but not by much. Okay, so it's pretty accurate. If you look at the GPS again, you're looking at GPS calculates speed and distance, and then calculates a time frame for that. So when you look at traveling, say billion miles away, 1 billion miles away. Well, at 186,000 miles per second, okay, you need to reach that distance in very short time. You will reach it in very short time at 186,000 miles per second. If you figure that number out, multiply it into a billion miles, okay, away, then it's only going to take you a few seconds to go a billion miles at 186,000 miles per second. So I really think that scientists and these physicists, they really need to start wrapping their head around things a little bit better, and maybe tightening something up like a few screws, because they're really not making a lot of sense in how they explain things. And the thing is, we really honestly don't know how long in time frame a light year is, right? And how are they calculating that and turning it into a light year? Because you need distance and you need speed is going to equal your time frame, okay? So if that is a constant everywhere, then it shouldn't be that difficult to figure it out, except that I really don't think a light year, for example, of distance is going to take you a year to get there, because that by itself is not, I don't see it being relevant, because you need the speed, you need the distance, figure out the time frame, and then that'll tell you how long. So who knows, maybe they could be right, maybe they could be onto something, but a light year would be 1 year. That's how they're classing a light year away from us, because the nearest star is X amount of light years away. It's going to take us, like 1,000 years to get there, at the speed of light. And going beyond the speed of light, they say, is something that's impossible, which I think is garbage. It's only impossible because we make it impossible. That's just it. I mean, they say you need a bigger ship to get more energy, and that's not true either. You just need a kind of a power plant system designed so you can still keep the same type size of ship, right, that you're working with a much different power plant system or energy system to give you that accelerated speed. Because you can run any object at any speed you want. It's kind of like, let's take a pellet gun, right? Every pellet in each weight category, be it 7 grain, 9 grain, 14 grain, 22 grain, 30 grain, and so on, each have a speed limit at which they can go before they start to do what's called pellet tumbling, which means instead of your pellet being on a steady course and being able to spin properly, it will start to jiggle. And if it goes too fast, it'll actually start to flip and roll and tumble. So it becomes useless, right? So you can only push each pellet weight at a certain speed. So when you're talking about a spaceship, for example, going in space, you're not limited to how fast you can move that thing, as far as how fast it can really go, as much as you are limited to how fast you can safely go before it can tumble, right? And once it starts to tumble, flip, roll, you're screwed, right, at that point. So you got to take a look at that factor. So it's not that we're limited to how fast we can really move stuff. We do need to figure out what kind of power plant we can use in each ship category to find out what the maximum speed that ship can handle, right? And then you build upon from there. Now the other thing they're talking about is folding space using warp drive, because that's basically what warp drive is it's a form of folding space. You're not moving, but everything else, you're sucking in space and ejecting it at the back, and therefore you're becoming further away. So you're in a warp bubble, okay, is what they talk about. And I got some looking in to do on that theory too, because the way I kind of see things, you need to move one way or another. You've got to be moving away from the object you're trying to get away from, right? But then on the other hand, they say, when you move faster than the speed of light, you create time travel. So you just left Earth, 5 minutes ago, but really more time than that has passed on Earth since you left, and you're traveling at the speed of light for 5 minutes at 186,000 miles per second. Time didn't go anywhere. That's where I see it. Time did not go anywhere. You got somewhere quicker, you got further away from the Earth faster, but nothing for time passed on Earth any quicker. You left, 8 seconds ago. You left 8 minutes ago. You've traveled a certain amount of distance away from Earth. That's it. And Earth is still doing its thing, you know, and so it still counts 5 minutes, 10 minutes, whatever. Just means you're able to accelerate at a much higher rate of speed so you can get away from there faster. You're not creating time travel even accelerated past the speed of light. So even if you went twice the speed of light, okay, so 186,000 times 2, so that's 272,000 miles per second would be twice the speed of light, or warp 2, Captain. Okay, so at twice the speed, you could get from here to the moon in less than half a second. Okay, you got to be able to stop too, and that's the big thing. How do you stop? You know, going from punch and boom. You're not going to be able to do it, obviously, right? Even at the speed of light, you are going to make the trip to the moon at about 1.1 to 1.2376 of a second. Okay, so you're going so fast. I mean, it's ridiculous to try and travel to the moon that quick. Just total dumb, right? But going to another planet outside our solar system within a couple of seconds, you know, hey, I see no reason why you can't make it to any of the planets within a few seconds or even a couple of minutes. Maybe it's a couple hours, because you're talking about a big galaxy, right? Our solar system is only so big, right? And then we have so many planets within our own solar system. And then you've got to look further beyond that to our galaxy. Now, our galaxy, maybe it could take you 2 or 3 years, even at the speed of light, to get outside of our galaxy and hop into space towards some other galaxy, right? So what's in between, we don't know. Probably not much, right? So when you're looking at it from that aspect, I don't see any reason why, if we could build a ship that could go exactly the speed of light even, okay, and us being able to handle driving inside it, of course, which requires a lot of creative thinking there and how we're going to figure that one out. You know, I see no reason why at the speed of light that we can't travel, you know, in a reasonable amount of time to anywhere within our own galaxy. I see no reason why we can't get to any of those other planets in our own galaxy with anywhere from a few minutes to a few hours, a few days, maybe a few weeks, maybe a few months, depending of course how big our galaxy is. Because you got to remember too, you're going at 186,000 miles per second, right? So the trip to Mars, instead of being 6 months, is probably going to take you maybe maybe 5 minutes tops, you know, maybe less, you know. So that's something to consider in that. So right now, do we need to go faster than the speed of light? I'm thinking no, we don't. Do we need to go faster than the speed of light to get to any of the planets within our own galaxy within a reasonable amount of time without it taking 20 or 30 years? I think yes, we should be able to handle doing that without any difficulty. Okay, so that puts us into a galactic capable traveling system. Now, if you look at, there was an episode from Star Trek Voyager. They got whipped out of the Delta Quadrant, whatever it was, and they were like 72, was it 72,000 light years or some stupid number, or 72, yeah, it was 72,000 light years away. They got knocked out anyway, so it's going to take them like almost 100 years to get back, because their ship is capable of up to, you know, warp 9 point whatever, right? So each level of the speed of light is, you know, would probably be counted as a warp speed. You know, who knows? I don't know how they count warp speed in that instance, but, you know, still, you know, they have to go to create time travel. They have to have certain conditions, a specific amount of speed, etc., etc. But then that kind of throws it out the door of the faster you go, you still don't create time travel. And I still kind of, for now, I'm going to stick with that it doesn't matter how fast you go, you don't create time travel. Time travel is something that is a whole different sort of thing. Time travel to me would be folding space, for example. Say you needed to get 1 billion light years of distance and do it within an hour, okay? Well, you're not going to be going a speed that fast to be able to do it. It just can't be done under present laws of physics, especially not under ours, and probably many other civilizations out there. So what they need to do is devise a way to fold space. Hence, you've got to be able to take space and bring the 2 points together and shorten your time. Wormholes, for example, help assist on getting mass distances, but the thing is, we don't know when the wormholes appear, disappear, how long they stay stable, how stable they are, where they even are realistically, and what's on the other end. Excuse me. So if you want to chart a course, you have to know that wormhole where it comes out on the other end. So you need to chart your course from point A to point B, and you should be able to realistically get out of that wormhole at any point in time and change. But who knows if you can do that or not? We don't know that, right? But I really think taking a look at all this in a more realistic perspective is something that really needs to be done, because you really can't believe everything you see or read, especially on the internet. But even when it comes to TV and what these scientists talk about and physicists, a lot of this stuff I find I really don't see where they're understanding even what they're talking about. Especially when you come up to theoretical physicists, because none of their stuff is practical knowledge. I mean, they're taking their best possible guess based on whatever to say that our nearest star is in such and such a distance away, and it would take us thousands of years to get there at the speed of light. How do they really know that? Have they been there? No, but they have a theory that based on this, this, and this, that they should be correct. However, it is quite possible that they could be wrong. It's the same as your car speedometer, right? It could be wrong. So you can get somewhere quicker in less time at what appears to be the same speed. Now, when I look at my GPS in my car, all it measures is the distance from one satellite to another, and the 2 points. I'm sitting in Barrie, Ontario, or I'm sitting in Niagara Falls, Ontario, or I'm in Toronto, okay, at the time, and I got to get back home to where I live here now. So it's going to say, okay, we got to take this point here to this point here. If he travels at this sort of speed with no interruptions whatsoever, it's going to take this amount of time. Oh, but we can't do that. We got to recalculate, and for anything that could possibly be going on, slowdowns in traffic, rush hour, etc. Okay, now it's a whole new calculation. But as you're traveling, and you're traveling at that speed, and it says it's going to take you 4 hours at 100 kilometers an hour. Well, not all your areas are going to be 100 kilometers an hour, are they? So you're going to be slowed back to 80, down to 70, down to 60, some places 50, and then you can go travel back up again. So now you got to make up time. And you can make up time on a GPS. It just means that instead of going 100 kilometers an hour to make up the time, okay, because you've lost maybe a couple minutes, you're now going to have to travel at about 160 kilometers an hour, way breaking the speed limit, to still keep it at its first original calculation that it's only going to take you X amount of time to go from A to B, right? So, because it can't calculate and judge for all the different things that could be going on. So the time frame is kind of stupid. So when you think of being out in outer space, speed versus distance versus time, there's a lot you can't calculate for. So you could get somewhere even much quicker. We just figure relatively at 186,000 miles per second, you can travel 186,000 miles in 1 second at the speed of light. And the moon is 250,000 miles away, so therefore, once you get past the first second, you better lay on the brakes quick and hard so you can slow down, hopefully, so that you don't smack right into the moon, okay? Or go in one hand and out the other and wind up mush, okay? So you got to calculate these things. So if you really want to get to the moon that quick, hey, it can be done at the speed of light. So how do you get there in a couple of seconds? Well, start cutting back the speed. Chop the speed up into quarters. Okay, so if it's only going to be 1 second at 186,000 miles per hour, then it's going to take you 4 seconds at 4 times slower than the speed of light. Okay, so now you've got 4 second time window. Okay, now we got to slow it down even more, because 4 seconds, I mean, you got to get off the Earth's surface and go punching, boom, you know, and going that fast with modern day rockets, if it could be done, would probably blow a hole in the planet, all right, just trying to take off, because it's going to be so fast and so hard of a thrust system, and it has to virtually get you there almost instantaneously, because 4 seconds is not long. So now you got to keep reducing. So now you got to cut it up into 32 times, 64 times, 96 times, okay? And then find a good speed that's relevant that can get you there in, say, 20 minutes, right? Or even an hour would be acceptable. So how fast you need to get to the moon in an hour. So if you went that same speed, how many hours would it take you to get to Mars? How many hours to Saturn? How many hours to Pluto? Right, with nothing in your way to smash into you, okay? Hopefully not. Okay, how long would it take you? And if you needed to get, and now if you start looking at the further planets outside of our solar system, okay, then you have to start looking at, okay, this planet is about probably the same distance that it was from Earth to Saturn. But now we're at Saturn, or we're on the edge of our Milky Way, and we got to get to this planet, and just from the edge to this planet is the same distance, so we know how long it's going to take us to get there, right? So putting in all these different calculations, figuring out speed, we should be able to design something realistically, guys, that is going to get us to anywhere we want within our own galaxy. And it could be a matter of days, weeks, maybe months. Maybe it could take a year. Maybe it could take 2 years, maybe 3 or 4 years to reach the farthest outermost part of our galaxy all the way around. So every possible angle. And we're not the center of the universe. We're not the center of our galaxy either. We're just like in the solar system here, whipping around the sun, okay? So we're not the center of anything. But you got to draw it as if you were. Okay, so in our Milky Way, where is it in that galactic belt of the galaxy? And how far to go from here to here? Then we just got to calculate, okay, well, if we can make it to the moon in 5 minutes, if we can make it to Mars in, like, 10, 15 minutes tops, well, then we should be able to get from here to over here at the outer reaches of our galaxy on this point to this point. Now, if we want to go from this point over to this point, well, now it's going to take a little bit longer, unless we increase our speed. And how much do we need to increase that speed in order to make that trip in, say, the same amount of time it takes to go from here to this part, or here to this part, okay? So we need engines capable of doing that, so we need a proper power source, fuel cells, whatever you want to do, and we can do all that, and still not even have to hit the speed of light to do it. And that's the nice thing about it, because you don't have to hit the speed of light, because it would be impossible to hit the speed of light and not get squashed going to the moon in 1.1 of a second. It would be impossible to go from Earth to Mars at the speed of light without getting squashed, right? So there's not enough time from start to slow down to achieve getting slowed down enough so that you can get into an orbit around Mars or around Saturn. So you need to recalibrate all your speeds and put realistic time frames on. How long does it take you to slow down this craft? And how are you going to slow down the craft? Shut the engines off and let it glide? No, you're still doing a crap load of speed, so you got to slow it down. So reverse thrusters, basically. So you need forward and probably other engines to be able to decelerate you to a slow enough speed so that you can get yourself into an orbit. So you got to do that in a reasonable amount of time. It's just that none of this stuff is impossible. That's the thing, and it can all be done. And I'm sure we have enough technology around right now to do a great percentage of it. I'm sure we have more than enough technology right now that we could get outside of our solar system, travel to other parts of our own galaxy, and there's billions of planets in our own galaxy to explore, right? I'm sure we can do that. I'm sure in this day and age we have enough technology by now, we should be able to pull that off. If we don't, well, hey, maybe it's going to take a little bit longer. But we know that escape velocity is like, what is it, over 17,000 miles per hour? So we can definitely pull that off in the space shuttle. So if you take that speed, okay, of the space shuttle when it has to leave an escape velocity of Earth and its gravitational pull, okay, just to get out of the planet and into space, how fast do you think you would be going at the same amount of throttle in outer space? Because there's less gravity in space than there is on Earth. On Earth, you can jump up and down on all you want. You're down as fast as you go up, okay? So you come down pretty quick. In outer space, you're not under the same laws of physics anymore. So now even the weight of your craft is much lighter. It's kind of like when you're at the bottom of the ocean, you can lift a really super heavy object without a lot of effort, right? But as the closer you get it to the surface, the heavier that sucker gets, because now you no longer have the buoyancy of the water helping you out, etc. So in outer space, you're in that same position where you've now left the surface, which is Earth. You've gone up into outer space, which is the big ocean, right? So now you're super light in comparison. So now your speed could be amplified possibly at anywhere up to maybe 20 times that speed maybe. Okay, I don't know the actual speed, but it's going to be super accelerated regardless, because you have squat for gravity out there in comparison to being on the Earth. There's a huge, massive difference. So the exact same weight object now becomes much lighter. So now when you take the theory of building a bigger machine with bigger engines, okay, you're going to get to the point where it's going to be, being in space is kind of like being like that big, you know, being on Earth. It's full gravity and you're like, "Bleh!" Okay, that could get to that point, because you're trying to go bigger and bigger and bigger to go faster and faster and faster. You don't need to go bigger and bigger and bigger to go faster, 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 right? But you need to have enough weight with the speed that you're able to obtain to not cause your projectile, which is your rocket ship, okay, whatever shape it may be in, to cause it to do this, the tumbling effect, right? Like the pellet, right? You shoot the gun, the pellet leaves the barrel at X amount of miles per second or per hour, you know, and if it goes too fast because the pellet's too weight, eventually the pellet does one of these, okay? So your spaceship is under the same laws of physics. If your ship is a certain shape and a certain weight, it can only withstand being on a straight-on course, or even following courses like this, whatever, in this case of a rocket ship, without tumbling and going, okay? So you look at it from that aspect. How fast can each shaped and weight class of vehicle actually realistically travel in miles per hour or miles in a second, you know, so that it doesn't get self-destruct and you don't turn into a topsy-turvy machine, right? And that would really suck, because you'd be really dizzy. Because then once you start into that tumble, there's really no stopping it until you shut the fuel supply off somehow, until it slows you down enough that you rebalance out, and then you'd be going, well, you know what I mean? So anyway, that's my ideas, my theories on that one, as far as, you know, traveling the speed of light or faster, results, okay, whatever you want to call it. Anyways, thanks guys for watching, and we'll catch you on the next video for sure.